Okay, class 11. So in the last video, we discussed the basic things about friction, and we also saw that friction basically is of three kinds: static friction, sliding friction, and rolling friction. Now, sliding friction and rolling friction are together also sometimes called kinetic friction. The word kinetic means motion, in motion. So, in some books, therefore, you might see friction is of two kinds: static friction and kinetic friction. So, don't get confused there. Alright, so after discussing the introductory things about friction, let us give a look at the laws of limiting friction in this video. Now, what is this limiting friction? Limiting friction, mind you, is static friction, and it is the maximum value that static friction can have. So, limiting friction is the maximum value of the static friction when the body, under the influence of an external applied force, of course, is on the verge of movement. The body is just about to move under the application of an external force. Okay, so the force of friction, or rather the maximum value of the static friction which acts then, is what is called your limiting friction. So let us give a look at the three laws of limiting friction. The first one says the magnitude of the limiting friction depends upon the nature of the surfaces in contact. And it further says it does not depend on the area of the surfaces in contact. So remember, the force of friction on the whole depends on how rough or how smooth the surfaces in contact are. The rougher the two surfaces in contact are, the more will be the value of the force of friction. And the smoother the surfaces in contact are, the lesser will be the value of friction. That is what is meant by the first statement over here. The force of friction, or more precisely, the force of limiting friction, depends on the nature of the surfaces in contact. And the second statement, it does not depend on the area of surfaces in contact. So what it means is, let me show you this. So I have this piece of tile over here, and I have this small glass, what do I call this? Butta. Okay, or I don't know what this is called. Glass box. So I have this tile here and I have this glass box. Now, so there is a certain value of force of friction that acts between these two surfaces when they are in relative motion. Now, if this glass box was of a bigger size, made up of the same glass material, and we had a tile of a bigger size, of course, then also when this glass box of a bigger size would move on this tile of a bigger size, of course, the force of friction acting would still have the same value. The force of friction does not, mind you, depend on how large this area of the surfaces in contact are. The force of friction is independent of that, remember. So that is what the first law of limiting friction is telling us. The second law tells us the force of friction acts tangential to the surfaces in contact and opposite to the direction of motion. This we've already checked actually in the last video. So if this is the surface over which a body is moving, the body is moving towards the right hand side. Okay, where does the force of friction act? The force of friction acts here, and it's acting tangential to the surfaces in contact, as you can see. Okay, or parallel to the surfaces in contact. And it of course is acting in a direction opposite to the direction of motion of the body. This we've already checked in the last video, and you can check here also. So this is your, so to say, F of S represents your limiting friction, that is the maximum value of a static friction, and this is the direction of motion of the body. So this is about the second law. The third law tells us the limiting friction is directly proportional to the normal reaction, capital R. So what does this mean? Now this body over here, excuse me, of course I'm not infected with coronavirus, alright. one thing. Let me erase the upper two laws. I hope you've copied this. You can pause the video and copy this, and let me show you what this third law is trying to tell us. So I'm erasing the first two laws, and let me draw the picture over here. So here is a surface over which this body is about to move, or rather on the verge of movement, because of this force F acting on it. But mind you, this force capital F is not enough to make the body move. Like I already mentioned, the body is on the verge of movement. So this is actually a free body diagram. So what are the other forces acting on this body? The other force acting on the body is, of course, its weight. If its mass is small m, then its weight is mg, where g of course is the acceleration due to gravity. The other force acting on it is capital R, where capital R is called the normal reaction. The word normal actually is a mathematical term. Normal means perpendicular. Since this force R is always perpendicular to the surface, so therefore it's simply called the normal reaction. And these two forces are equal and opposite to each other and acting along the same straight line, so therefore these two forces, they cancel each other out. What is the other force acting on the body? The other force acting on the body, of course, is our force of limiting friction. Since the body is on the verge of movement, so the force of limiting friction. So this third law is telling us that the force of limiting friction is directly proportional to the normal reaction. So what does it mean? It means that more is the weight of the body, more will be the force of friction, or more will be the force of limiting friction acting on the body. You must have of course experienced this. Okay, I have a body having a very light weight. It's very easy for me to displace this body. Why? Because there is a very small value of force of friction that acts when it comes to this body, because this body has a very small weight. And don't forget, more is the weight of the body, more is the normal reaction. Less is the weight of the body, less is the normal reaction. These two forces, they have to be equal and opposite. Alright? And it will be very difficult for us to push a cupboard. Why? Because the cupboard has more weight, and thereby it will have more normal reaction, and hence more will be the force of friction acting on it. Okay? That is what directly proportional means. Directly proportional means, if I say A is directly proportional to B, what do I mean? What it means is, if one increases, the other has to increase. If one decreases, the other has to decrease. Now, if only these two criteria are fulfilled, mind you, we cannot say A is directly proportional to B. We cannot say that. There is also a third criteria needed to be fulfilled, which is, if one becomes 0, the other has to be 0. So only if these three criteria are fulfilled, mind you, then we say two things are directly proportional, which of course is true in this case. If there is no weight of the body, no force of friction acting, of course. Okay, so this relation can be rewritten as, or f of s is equal to mu s into r. Now we know a proportionality sign can always be replaced by an equal to sign, provided we add some constant. And the constant of proportionality here, mu s, has a name. It is called coefficient of static friction. Just called coefficient of static friction. Okay, so this is the first important equation that you need to remember when we talk about friction. From this very equation, of course, we can write, let me write it over here, mu s is f of s upon r. So from here you can define the coefficient of static friction. So if you are asked the definition for coefficient of static friction, you can write it is the ratio of the force of limiting friction to the normal reaction. So this is about a body on the verge of movement, static but on the verge of movement. Now once your external applied force increases even slightly, by a very slight amount also, what happens is the body now starts moving. In this case it starts sliding. So when the body starts moving, mind you, then we no longer talk about static friction, of course, thereby we no longer talk about limiting friction, and hence we no longer talk about coefficient of static friction. Get this thing very, very clearly. Because when the body starts moving, then after we start talking about kinetic friction. Okay? And mind you, if f of k represents the force of kinetic friction, then this kinetic friction is smaller or lesser than the value of the limiting friction. By a very slight amount, by a very small amount, but still the force of kinetic friction will be lesser than the force of static friction. I don't know whether you've experienced this or not. Try to push something heavy, maybe a table. Okay, initially it will be difficult for you to push it. Alright, now you go on increasing your force and it's on the verge of movement, and you apply your maximum force and the body starts moving. To make the body move, you have to apply a greater force. Okay? Once the body starts moving, you don't have to apply that amount of greater force to keep it moving. Why? Because the force of kinetic friction is lesser than the value of limiting friction. I cannot show that thing to you here in this video. You have to experience this. Okay, and you will see that it will be easier for you to keep the body moving than to start its motion initially. Simply because of this fact. And once the body starts moving, like I said, we talk about kinetic friction, and when we talk about kinetic friction, for kinetic friction also the same three laws for limiting friction are valid. And for kinetic friction also, we can write kinetic friction is directly proportional to the normal reaction. That is, greater the weight of the body, more will be the kinetic friction. And thereby, talking about kinetic friction, we get kinetic friction is mu k into r, where mu k is now the coefficient of kinetic friction. Let me erase this law here. Mu k will be your coefficient of kinetic friction. And if you have to define mu k, the coefficient of kinetic friction is the ratio of the force of kinetic friction to the normal reaction. Okay, very similar relations, but this is for kinetic friction, this is for static friction or limiting friction. Now, let me just give a look at this graph. We have a graph. I hope you've copied this. You can pause the video and copy this, okay? Because I'm going to erase it now. So there is this graph that you need to draw. You might get to draw it in the exam also. This is the applied force or the external applied force. Applied force, capital F, and this is your force of friction along the y-axis. Force of friction along the y-axis. So initially what happens is when you increase your force of, so initially what happens is the body is not moving, you apply a small value of force, applied force, the body of course doesn't move. The moment you apply the force, what happens? A force of friction comes into play. A small value of force of friction comes into play. Okay, you increase your force of applied force slightly, the force of static friction also increases proportionally. Alright, so what happens is, I increase the applied force, the force of friction also increases. I increase the applied force, the force of friction also goes on increasing until it reaches a maximum value. This value is, so to say, F of S, the value of limiting friction. Then after, so up to here is, you're applying a force here such that the body is on the verge of movement. Now, you increase the applied force just slightly, what happens is the body starts moving, and then we talk about kinetic friction. It has to be parallel to the y-axis. So it has to be parallel to the y-axis. So this is it. And as you can see, this is your value of Fk, or rather, this point here is the value of Fk, the force of kinetic friction. And you can see the force of kinetic friction is lesser than the value of limiting friction from the graph.